Welcome back, everybody, to this session of the machine learning course for the Erasmus Plus program. And the topic today, as also announced in different emails, and please apologize for not having had the lectures last week because I was away for a meeting. So we're going to compensate for that with having lectures today on December the 12th and tomorrow as well. The lectures will be recorded as always. And if you scroll down to the lecture plan, the lecture today is about solving differential equations with neural networks. However, we are going to use the first part of the lecture to discuss again and repeat topics which we had last week. And we're going to look at the link between the backpropagation algorithm and automatic differentiation. And then we are going to move over to the solution of differential equations with neural networks. So this will be an application of what we have done to a type of problem which is highly relevant for the natural sciences. And this forms also kind of basis for what today many people call physics-informed machine learning, where in particular applications to differential equations like Navier-Stokes in fluid mechanics, or even quantum mechanical many-body type of problems like solving Schrödinger's equation for many interacting particles is a topic which is under great interest, and is also there are also lots of new developments taking place there. And you will find after the lecture, you will find the videos and also the handwritten notes. So this is actually what is session 8 in the lecture link. I'm going to use the Jupyter notebook as usual, but before we do that, I wanted to go a little bit back to what we did last week. So last week, or on November the 27th, we discussed the setup of the so-called backpropagation algorithm. And in that specific case, what we had was a given cost function at the final layer of a neural network. And I will repeat some of this by going back to the whiteboard quickly, rather soon now. And we defined this constant delta. And with that constant delta for the final layer L, so uppercase letter L stands for the last layer, normally also called the output layer. And then we could propagate back again this error or this constant delta, which is then derived using the chain rule. And with that, we had the update algorithms for the weights and the biases for each singular layer. Now, what we did last week was also to discuss the specific implementation of the algorithm to a classification problem, but we can easily well apply this to a regression type of problem where we want to fit a specific continuous function. But let's go back to the whiteboard and take a look at the basic equations which we set up last time. So I'm going to switch to the whiteboard. So let me do that. So when we now defined our neural network, what we had was the following graphical representation. And we used the setup of the neural network in order to find the define the so-called backpropagation algorithm, which is just an implementation of the chain rule. So what we had when we now set up this neural network here is the following. So let's just write this down here. This is the basic layout. We have an input layer, which we label with the X for the input variables. So this could be a vector, it could be a matrix. Normally, this would be represented by our typical design matrix. This is then fed into the first hidden layer, and it's coupled with a weight. So we have a 1 here to indicate that this is the first hidden layer. And this produces an input, which we called as Z1. So this can be a vector, it can be a matrix. we feed in a so-called bias, which is normally set to a non-zero variable in order to often avoid that the network stops training in case the weights are accidentally set to 0. Now this produces an output. So this C is now fed into this activation function. And these activation functions could be given by different types of functions. They could be the same for all the hidden nodes which we have. So this will be what we have here, would now define the output from the first hidden layer. So we define that by a label A. So A1 stands for the output from the first hidden layer. So let's mark this one like this. So what we have here is in essence what comes in and what comes out from the first hidden layer. And the way we can write this is that this function A1 is now given by this sigma of 1, and this has as an input this Z1, which then depends on the weights and the biases. Then we defined also this theta of 1. That is a collective container for the unknown parameters W, which are called the weights, and the unknown parameters B, which are called the biases. So these thetas are the parameters which we want to define by the backpropagation algorithm. And then this continues now to all the different hidden layers. So we would get into a new hidden layer. So we have a new set of weights, W2 here. We have a Z of 2 here. This receives an input, a B of 2, the weights and the biases. And then we have an output, which is modulated by a new activation function. So these functions, sigma here, normally called the activation functions. And that produces a new output, which we call for A2. So this will be layer 2 we have here. So this will be our second layer. And then we can continue like this till the final output layer. So we can just mark this with different dots. And then at the end, we have the final output layer, WL, that feeds into the final input to the hidden layer. So the hidden layers may have different nodes. The architecture of the network is defined by the number of hidden layers, the number of nodes or neurons or units in a given hidden layer. And then we have the activation functions as well, which define the architecture of the system, or this is normally referred to the model. So the number of hidden layers, number of nodes, and the type of activation functions define our model / architecture. And this is then sent in to the final activation function. And the activation functions at the end, they can be different from the activation functions in the hidden layers. And the activation functions at the final layer, they are typically defined by the type of problem we are looking at. So if we have a binary classification problem, a typical output layer would have the sigmoid function as just one example. Or if we have many classes like this 100 numbers, and where we have 10 types of 100 numbers from 0 to 9, then you would have 10 output nodes. If you're dealing with the output of a specific function, you could have some x values which are fed in, and these x values could be the positions of an object in a three-dimensional space. So this could be x, y, and z, the different Cartesian coordinates, and that would produce a final output value. So this would be the final output value, which we call for an A of L. So this final layer here, which you see now, is normally called the output layer. And this output, which we produce here, that is sent in to the cost function. So we have a cost function C, and that value is compared with the target values. So the target values are the observations which we have. So this is the basic layout of a neural network. And what happens then is that we have the final output. So the final output from the network. This is this variable A of L, and that is a function of the input known values and all the unknown variables theta. So this theta, which you see now, is a collective container for all the parameters which we have. So this will be the unknown parameters in the first layer. It will be the unknown parameters in the last layer. And this goes all the way up to the final layer. So these are the parameters which we actually want to define through the training of a neural network. So that will contain the weights in the first layer, the bias in the first layer, and then we move on like this with the weights in the second layer, the bias in the second layer, till we reach the final layer where we have the final weights and the final biases, B of L here. So these are the parameters which we now need to define. And these A of L's are fed into the cost function. So we have a cost function which will now depend on this output from the network. And this will be compared to the variable t. And then what we need to do then is to define the parameters by now calculating the gradients. And we would typically start calculating the gradients at the final layer. Now, the typical cost function, if we now write this as a C, so this is actually a function which we now want to be given by these unknown parameters, theta of L. So let's just rewrite it like this. So we have a theta, which are the unknown parameters. This depends on the input variables x. So this theta, which you see here, are now the collective container for all the unknown parameters. And this is also a function of the target values t. So if we now look at the function c of, and let's just write this as A of L, the typical function is something which will depend explicitly on the variable A, but it depends then implicitly on all the unknown parameters theta. So what it means then is that what we have is something, if we now are looking at a regression type of problem, this could be the mean squared value. So we have a t minus this A of L as a function of theta and as a function of x, the input variables. And we could have now the mean squared value. So we have the norm 2 squared. And alternatively, we could also have a so-called shrinkage parameter of the type of the ridge type where we have the norm 2. So this would now contain something like this squared. So we have a norm 2 of the shrinkage parameter, and this is normally squared. So this would correspond to what we discussed in connection with the ridge regression. So this is a typical case of a cost function. So this is an example for a type of regression problem where we now want to fit a given function to the data which we're fitting in. If we're dealing with a classification problem, this could, for example, be the so-called cross entropy. Now, what we end up doing then is to have to calculate the derivative. So we want to now drive these derivatives as a function of these variables and starting at the final layer. And this is where we actually end up with the backpropagation algorithm. So what we define then, so this is what we want to calculate. And this is obviously a function of all the previous values. So which is a function which ends up being a function of all theta values. So we would have the first layer, the second layer, and so on to the final layer here. Now, note as well, if we go back to the previous equation, if we look at the previous equation, what we have when we are setting up the cost function is a function which normally depends only on this A of L, which means that we have to use the chain rule in order to calculate the derivative at the final layer. So if we look at the expressions at the final layer, what we need then to do is to use the chain rule. So if we take this d of the cost function of d of theta of L, what we end up with then is first a derivative. So this is basically just us applying the chain rule, because the function c depends explicitly on A of L and only implicitly on the parameters theta, which again contain the weights and the biases. So now we're just writing this in terms of a common container, theta, for both the weights and the biases. And then using the chain rule, what we have then is that we have this d of, sorry, not that. Using the chain rule, we get d of A of L. And this is a function of, we know that A is a function of this z. So we would have a z of L. And then finally, we know that this z, the input to the final activation function, is now given by this variable z, which then again depends explicitly on the different parameters. So this is the one which now depends on the parameters theta. And we know that this z of L, when we write it out in terms of a vector matrix relations, so we would then have a input from the previous layer. So we have an L minus 1 plus the biases L here. So C can be a matrix or it can be a vector, depending on how we have defined the network. So here we have the explicit dependence on the parameters theta, which again is given by the weights and the biases. So the weights and the biases, which we have here, they are actually described by this common container. So that means that we would have to calculate a derivative here for the weights and the biases. Now, these functions which you see here, this one here, the first function, which is given by this term here, is something which now defines this parameter delta, which we set up last time. And then finally, we would have this final parameter here, which when we take the derivatives, is going to give us either a derivative with respect to the weights, and then this parameter will simply be equal to that one, or in terms of the biases here. So if we now set up the equations, what we end up with is a parameter delta and of L for the final layer, which then ends up which is given by the derivatives of the activation function in terms of the last layer. And we're putting a prime here to indicate that this is a derivative. And then we have the derivative of the cost function with respect to the output from the final layer. And this function which you see here, this one, is nothing but the derivative. If we go back to the equations which we had here, this is nothing but this derivative which you see here. So if we go back again, this is now the same as d of A of L of dc of L. When we have these equations, then we can go back and find this parameter delta for all the previous layers. So if we now look at L going down to L minus 1, L minus 2, and all the way down to the first layer, what we had then is a delta J of L. And now we are breaking this down in terms of a given component, J, for a given node. And this is given by the sum over K from, and this was just an application of the chain rule, of L plus 1, the results from the previous layer. And then we have a weight, WK of J of L plus 1. And this is multiplied by the derivative of the activation function of Zj of L. So this is a function which we need to implement, and then we can train the weights and the biases in an individual layer. So this is given by the following update algorithm of Jk of L, and then we have a parameter eta, which is the learning rate. And we have a delta J of L. And this is now multiplied. So we're putting this in parentheses to indicate that these are the specific layers. And this is multiplied by the output from the previous layer of L minus 1. So we need to take care of all these pieces of information here. And then we have a Bj of L, which is then updated. So this is simply us setting up the typical gradient descent algorithm minus eta, which is the learning rate, multiplied with this delta J of L. So these are the equations for the gradient. So every time we perform a forward pass, then we have a backward pass. And then in the backward pass, we update the gradients. And then we repeat this a given number of iterations. So typically this could be 1,000 iterations, it could be 10,000 iterations. And the number of iterations can then be accompanied by a test, a convergent test, where we typically could let, for instance, the derivative at the final output layer to be as close to zero as we can after a given number of iterations. So one iteration means one feed forward pass and one back propagation pass. And in each case, we update the gradients only once. And then with the new gradients, we perform a new feed forward pass. We get a new output to the final layer, this one. And then when we have the new output, we can calculate the derivatives again at the final layer, and then we propagate back again. And then we have a new update of the weights and the biases, and then we go back and forth this a given number of times. And that defines the number of iterations. So in essence, what we end up doing then is the following. So the back propagation is nothing but us actually applying the chain rule again and again and again and again. So what we can do then, if we now want to calculate the derivative of the cost function at the layer L minus 1, this is simply given now by dc of d of theta of L, and then we have a d of theta of L multiplied with d theta of L minus 1. And then we can continue this using the chain rule and just go back and back and back again till we have the final layer. And then continue till first layer. So normally, and one of the reasons why we do the back propagation this way is that typically when we look at the final output layer, this final output layer has normally a much lower dimensionality than many of the first, second, third, and so on, or the just intermediate layers. So if you think of a regression case, you have just one output for one given function value, which means that then your output is just a vector in one dimension, and we just want them with one entry. So it's a vector of length 1. If you then feed in a set of input variables, suppose you're in one dimension and you have 100 input values, then you get 100 output values, and you will train your network on these 100 input and output values. If you're dealing with a binary classification problem, you would also just have one type of output. It's either 0, 1, or -1 or +1, depending on how you define the output. If you have a typical classification problem with more categories / classes, then you end up with, say, if you're looking at the MNIST case, where you have these handwritten numbers from 0 to 9, then you have 10 classes. So then you would have 10 output nodes. That means that the dimensionality which you have at the final layer, the number of possible variables here, the length for that vector or matrix is actually smaller compared to the typical dimensionality you encounter in the intermediate layers, which means that the number of derivatives you calculate at the end is much smaller than what you would typically calculate if you were to start from the first layer. So that means that when we are setting up a neural network, we're actually back propagating the derivatives. So this is something which is very close, or it's actually the same as automatic differentiation in what's normally called the reverse mode. So let's now look at the connection between the backpropagation algorithm and automatic differentiation. So we are going to look at automatic differentiation for a simple example now. Differentiation, which we introduced differentiation in what is normally called reverse mode. And that is the same as our backpropagation algorithm. So automatic differentiation means us using the chain rule, and this is normally applied to a set of well-known functions to which we can calculate the derivatives. And by using backpropagation automatic differentiation with where we can express all the derivatives in simple functions, then what we end up with is an algorithm where we can calculate to numerical precision the derivatives. So automatic differentiation is not symbolic differentiation, which you could have with a Mathematica, for instance, or you can use MATLAB with symbolic differentiation, because often these algorithms give you equations which can be pretty lengthy when it comes to numerical implementations. It is not the same as you setting up a finite difference scheme for calculating derivatives. So let's first say what it is not. So it is not symbolic differentiation. And it is not an implementation of finite difference calculations. So finite difference means that if you have, let's say, the first derivative of a function f of x, this is often approximated if we are thinking of the standard Euler formula by something which is given by f, calculated at a value x plus a delta x minus an f of x, and this is divided by delta x. This is a finite difference equation. You can have more refined equations for this when you move on. But these kind of methods which you see here, both the symbolic differentiation, which can often lead to very lengthy equations, or the standard finite difference, which normally gives you a result, which depends on this approximation you make, delta x, with a delta x a step size. These are not methods these methods are actually not the same as automatic differentiation. So to understand what automatic differentiation is, let's now take a look at an example here. So we are going to look at an example which we can display graphically. So we have a function f of x, which is given by x squared plus the exponential of x squared. Now, if we now look at this in a very, very brute force way, we can think of the following number of operations which are needed in order to calculate it, number of operations. So we have 1. We need to calculate x times x. So this is one floating point operation, one multiplication. And we are going to assume now that every floating point operation is taking the same amount of time. So that means that when I calculate the exponential, I consider that as one floating point operation, which is in principle not correct, because calculating the exponential of a function takes much more time than just doing multiplications, additions, subtractions. So just keep that in mind. But now we're just going to look at this as one floating point operation. Then the next type, if we now do this in a very brute force way without thinking, so we have an addition of x squared plus the exponential here. So that is one more flop, one floating point operation. And now I'm doing this in a very stupid way. So if I look at my exponential here, I have x squared. So I'm recalculating x squared. this is actually, as I said, it's a very brute force way. We are not thinking. And one of the problems with this approach, which I'm mentioning, is exactly what a typical expression you would get from, let's say, Mathematica. If you take the derivative of this function, you will include something which contains the exponential of x squared. And Mathematica or MATLAB or SymPy, they allow you to translate the expressions you have for the derivative into a code, either in C++ or Fortran or Python. And then it will normally translate directly these operations without thinking of making simplifications. So this would contain the exponential plus x squared. So if we are doing this in a very brute force way, this is two floating point operations. And then at the end, we have the square root of the argument here. And the final argument contains now 4 floating point operations. And if the square root takes the same amount of time, which is not correct, but we're simply setting these up as floating point operations, then what we have in total here is 5 floating point operations when we add it up. So I'm going to put an S here. So this is floating point operations. So it's not floating point operations per second, but it's just a number of floating point operations. So this is not a very smart way of setting up things. If I then calculate the derivative of this function, the way it would come out from an algorithm like MATLAB or symbolic Python can also do the algebraic manipulations of these expressions. There's a SymPy package in Python, which you can use. So if I do that, I would get an expression for this function with respect to x, which is now given by x of 1 plus x squared. This is actually the output, which also symbolic Python would give me. And if I use this expression here with symbolic Python, it would simply translate this one into a code in Python or C++ or Fortran, and it would translate it exactly as it stands. So if I now want to do the counting, the brute force counting without thinking, and I write a code where I recalculate x squared as an argument to the exponential, so the brute force counting here is going to give me 10 floating point operations. So this is actually quite a lot. Now, what I could do now is instead of doing this, I could now start thinking a little bit. And what we will see now is that we are going to simplify this type of equations so that the calculation of the derivative is going to take essentially the same number of roughly floating point operations as we would have with the calculation of the function itself. So let's take a look at this in a graphical way. So we would have an input x. This is the input. Then we have an operation here where we square it. So I'm just putting a dot here. So I'm just having the function value squared. This produces now an intermediate variable, which I'm going to call for a. This intermediate value is now used to calculate an exponential. So I'm just writing this as an xp. And this produces the new variable, which I'm going to label as a b. Now, this is now added with this value a here. There is a plus operation, so I'm adding x squared plus the value of b, the exponential. So I'm adding these two here, and that gives me a new variable c by the addition. And then this c here continues into a new operation, which is the square root. This produces a new variable, which I'm going to call for d. And this one is now going to be equal to the final value f here. So a is simply x squared. B is the exponential of x squared, which is the same as the exponential of a. So I have pre-calculated this variable. C is nothing that a plus b, which is indicated graphically here. And this function d is simply the square root of c, which is simply the same as f of x. So this example is just a plain example which we are going to use to indicate how we can set up the automatic differentiation using the chain rule. So if we now look at these expressions which we have, what we have now is a d of a dx, which is simply given by 2 times x. I have a db dx, and now I'm using the chain rule here. So let's just do this intermediate calculation, and then I have a d of a, and this is the same as a d of a, sorry, of dx. If I then look at dc here of dx, this would now contain of dc dA of dA dx plus dc dB of dB of d of x. And the last one here, where we see now that dc of dA is the same as dB of dc equal to 1 here. So that means that my dc dx simplifies to a dA dx plus a dB dA of dA d of x here. And then I have the next one, which is d of d of x, and that is nothing but d of d of dc of dc of d of x. And this is also the same as our function d of f of d of x. And if I put everything together here, this is nothing but 1 over 2 over square root of c of dc dx, which we calculated earlier. So if we now want to compute d of x, so what we want is obviously df of d of x. Now f now depends on all these intermediate steps. So if we now work ourselves backward here, so we start with the first derivative with respect to d. So we would then have a df of dd, and that's just equal to 1 because f is equal to d. Then I move to the next step in this graph. So I have a df dc, which would simply be given by df of d, and this is a chain rule again. And now you see the similarity with a neural network. And this will be given by 1 divided by 2 over square root of c. So if you go back to the neural network, this is exactly what we are doing now. So let's go a little bit back to what we looked at earlier with a neural network. So if I now think of my derivatives at the layer L-1, these would be simply given by the derivatives using the chain rule here. And you can see that now if you start at the first hidden or output layer. So at the output layer, I'm also using the chain rule. And what I have now is the derivatives of the variables at the output layer, which are now given by the explicit output value. And then the explicit output value depends on the input to it, which then depends explicitly on the unknown parameters. So this would be the first stage for the output layer. This would be the final layer, this function df dd as we put it up. And then we can step ourselves backward by simply using the chain rule here. So the back propagation here is going to be exactly the same thing as automatic differentiation in the reverse mode, where we actually start with the derivatives at the final point. And in our case, we have defined this variable d, which is the same as the function f. And then we can break this d down in terms of the different variables, c and b and a and d finally here. So if we now look at the derivatives which we are going to need in order to set this up, so we need also this df with respect to b. which is going to be df, and you see now how we use a chain rule to back propagate, dc db, and this is the same as 1 over 2 over square root of c again, when we just use this simple example which we ended up with. We need also df of d of a, and this is now given by df, db, and then I have a db of d of a, plus df dc of dc with respect to a here. And if I put everything together, this is going to give me 1 over 2 over square root of c, and then I'm going to have 1 plus the exponential of a. Finally, what I have is that df of d of x is going to be given by this df of dA of dA with respect to x. And if I put everything together, this is going to be given by x of 1 plus the exponential of a divided by the exponential of c, which, when I collect everything, is nothing but x of 1 plus this number b divided by the number d. Now, all these quantities, when I'm calculating my different expressions, so if you remember now that d is the same as the original function, which is x squared plus the exponential of x squared. If you now look at the number of floating point operations here, what I have, when all these quantities are pre-calculated, so what I said, if I pre-calculate everything, so this function which you see here, this is actually our b, this is our a, so a is pre-calculated, so that's one floating point operation. I add the exponential of a, so that's another floating point operation. I have the plus operation here, so that gives me 3 floating point operation, and then I have a square root. So calculating d is the same as 4 floating point operations. Then, if you now look at what I have for the derivatives, I have 1 addition. So b is pre-calculated because b was used to pre-calculate this exponential of a. So this is already known. I don't need to recalculate it. It's a quantity which I have pre-calculated. So I have 1 addition, and then I have 1 multiplication here. So that means that I have 1 and 2 floating point operations. Then the function d has already been pre-calculated, so there is no calculation here. And then I have a division. So I have 1 addition, 1 multiplication, and 1 division on a pre-calculated quantity. So the derivative now needs only 3 floating point operations when everything has been pre-calculated. So using this type of back propagation, which you see here, gives me, with pre-calculated quantities, so I have predefined these quantities here. I calculate them, A, I calculate B, I calculate C here, and I calculate D. So with those pre-calculated, I need only 4 floating point operations to calculate F. So that means that my calculation of F now, if I go back to the expression here, now requires only 4 floating point operations. If I look back at the derivative, which I could get from symbolic Python, which translates everything as it stands into a C++ code or Python code, just to give an example, then this would give me 10 floating point operations with everything pre-calculated and using the chain rule to calculate the derivatives and using the chain rule in a backward mode. Then what I end up with is only 3 floating point operations for the derivative. So if I were to not think and just let, let's say, symbolic Python translate my code, my analytical expressions into a code, then I would actually need 5 floating point operations for the function itself and 10 floating point operations for the derivative. So that means that I end up with 15 floating point operations if I don't think at all. If I use this back propagation algorithm, I would then get in total 4 floating point operations for the function itself and 3 for the derivative. So that's 7. So that's half of the number of iteration of operations which I need. So if I then want to use this, I can actually systemize it and set up an algorithm which allows me to calculate these derivatives by either moving forward, so I start with x and move to the final value, or I start with the final value and propagate back again. So after the break, we are going to set up the final expression for the final algorithm for automatic differentiation. So just to quickly recapitulate what we discussed before the break, we wanted to link automatic differentiation with back propagation. And we started with a simple example where we selected this function f of x. And then we went through what we would call a brute force calculation of the derivative. And if we don't think at all and just let, for instance, the symbolic Python translate this function into a code in Python or C++ or other languages, then if we don't think at all, this would correspond to us having to perform 5 floating point operations, where we have simply assumed that the exponentiation of a function and also the square root is just defined by one operation. This is not correct, but for this simple example, this is more than sufficient. So we would have 5 floating point operations for calculating that function. And then we could calculate the derivative and then let, for instance, symbolic Python translate this one into a code. And if no simplifications are made, this would give a brute force algorithm which corresponds to 10 floating point operations. Now, what we did then was to represent these operations graphically. So we would have an input x, and we calculate the derivatives of f, the final function, in terms of x. This is what we want. And we can actually calculate that as a chain of operations with different intermediates. So this function d, which we have here, is equal to f of x. So the derivative of f with respect to d is equal to 1, because it's equal to itself. And then we can continue with using the chain rule. So we would have f with respect to d. So we would then calculate the different quantities. We would need dc with respect to x, d of d with respect to x, and you can see now the chain rule being applied. So we could start with f here, which then we could back propagate all the way back to the final answer which we want, which is obviously df with respect to x. And by using the chain rule, we could actually back propagate this. So we could then get down to df db, df dA, which is given by this expression. And finally, we would then have a df of d of x, which is given by this expression, which simplifies to this. And if we now look at the number of floating point operations we have, when all these functions, which are now given in terms of simple functions like an exponential, it could be a cosine, it could be a sine, it could be a square root. So these are well-known mathematical functions from which we know how to calculate eventually derivatives. So back propagation and automatic differentiation, and automatic differentiation in particular, is a set of operations using the chain rule on known functions. And known functions then simply means multiplications, additions, subtractions, divisions, and different mathematical functions like sine, exponentials, logs, etc. With that, we ended up with 3 floating point operations for the function for the derivative and 4 floating point operations for the function itself, which is 7 compared to 15, which is a reduction by a factor of 2 or more than a factor of 2. So when you calculate these derivatives, when you set up everything graphically, you could obviously start with the input here and then go all the way till f. And that will be automatic differentiation in the forward mode. Or alternatively, we could start with f and then back propagate ourselves. And that would be automatic differentiation in the reverse mode. So the algorithm for automatic differentiation, we then think of this simple model. So automatic differentiation is a formalization of this simple example. And if we then assume the following, so assume that we have a set of functions. So we have different functions, which I'm going to call x1 up to some x of d. And these are so-called input variables. And these are input variables to f, which now contains x of d plus 1, of x of d plus 2, etc., up to x of d, so-called intermediate variables. And if we now look at the example which we have, where x of d now, so we have x of d1, and then x of d is the output. And if we go back to the simple example which we put up, we could think of x of 1 as the variable x. We could think of x, so in our case, d is equal to 1. So these are the input variables. We have only one in our case. So x2 then, since d is equal to 1, so x2 becomes a. x3 is equal to this variable b. And then clearly x4 has to be equal to c, which is a plus b. And then xd, which in our case is equal to x5, that is equal to d, and that is equal to f. So what we will do then is the following. So the algorithm here is now to have a loop for I equal d plus 1. So up to d, these are the input variables. And to the final variable d, then we would simply calculate these different x of i's, which are given by some function g of I, which then are in terms given by some specific functions p of d, or let's just call this px of I. And this g of I, they are elementary functions, and this is an x p of a. They are just the parent nodes of the variable x of I in a given graph. So if you now look at the algorithm which we would have, and translated in our simple example, it means that this g2 here, that would simply be given by the variable x. I'm just putting that as a dot squared. So that defines a. g3 would in this specific case be the exponential of a. So we will put in a here. g4 would simply be given by a plus b. So that would contain g2 plus g3. And g5 would simply be the square root of c, which is equal to d. And by definition, what we have then, so what we have then is that df, the derivative of the function we are looking after, at x of d is actually equal to 1. So the reverse mode is now simply given by the following. So that's given by a d of f dxi, and that contains now a sum, and let's switch page here, where we have x over x, a sum over x of j's, and then I have a df dxj of this dj and with respect to dx of I. And this x of I is simply given by this specific function which we have as an argument of x of j. So PA stands for parent function. And so this PAX of j is a set of parent nodes of xj in that specific computational graph. So if we then go back to what we had in this specific example, we would have a d of f of dd, which is equal to 1. And then we have a df dc now, which is simply given by df of dd. And then we have a d of dc. And this is by definition equal to 1. So when we look at that specific example we have, this is the square root given by 1 divided by 2 times the square root of c. And then I need my df with respect to b here. And that is obviously given by df of dc of db. And that is again 1 divided over square root of 2c. And then I need the same for df dA. And I'm just going to leave that as an intermediate case to you guys. And then when I set up everything at the end, I have df d of x, which is going to be df dA of dA of d of x. And in a simple example, this is nothing but x times 1 plus b divided by the variable d. So the automatic differentiation algorithm can be performed if we use this graph in what is normally called a forward mode or reverse mode. What's often used is a reverse mode. And when we have this reverse mode, what we end up with is a calculation where we start with the end product and then step backward. And this is the same as we would have when we implement automatic differentiation. Now, what I wanted to do now, after this excursion and linking automatic differentiation with back propagation, which both these methods are just simple applications of the chain rule, what I want to do is to say something quickly about the neural network calculations and wrap up a little bit about neural networks. And then we are going to dive into the setup of the solution of differential equations with neural networks. So let me now switch back to the whiteboard, no, to the Jupyter notebooks. And I want to bring up the Jupyter notebook from November the 27th, which is also linked up in the lecture notes as session 6. So let me just set that up. So I just wanted to repeat some of the things which we had last time, and then also say a little bit about how to use TensorFlow. So TensorFlow is a very popular library which can simplify life considerably when we're now setting up, let's say, a neural network. So for project number 2, if you wish to use TensorFlow, feel free to do that. PyTorch is another very popular library. So TensorFlow was released by Google in 2015. And it's one of the really more widely used libraries for deep learning. And it has an API, which is called Keras, which I'm going to show how to use now. Alternatively, if you're more familiar with PyTorch, which I think was released by Facebook in 2016, and it's being continuously upgraded. PyTorch is another of these popular deep learning libraries. Then for project number 2, where we are going to look at the implementations of neural networks to a specific problem, or convolutional neural networks, which is the topic which will come after we've discussed the solution of differential equations, then feel free to use TensorFlow with Keras to set up your neural network. Alternatively, if you want to write your own code, you have essentially the recipe in the lecture notes here to do that. And this is what we went through last time and how to set up a neural network. But what I want to do now is to move on to how you can use Keras together with TensorFlow. So the examples which I'm scrolling through now are the examples which we went through last time, where we actually building our own neural network code. And we found then, when we looked at this specific code, whether we use our own code or scikit-learn, which has a simple multi-layer perceptron model for a feed-forward neural network, essentially. Then what we found when we visualized the results was that we got with scikit-learn and also our own code as a function of the hyperparameter lambda and the learning rate, we got an almost perfect training on these handwritten numbers for specific values of the learning rate. So this would correspond to a learning rate of 10 to the minus 3 to 10 to the minus 2 here. And similarly, we have a pretty stable result as a function of the parameter lambda, the hyperparameter. And then our test accuracy was actually 99%. And this contains only one hidden layer with 50 nodes. And we use the sigmoid function as an activation function. And then the final layer contains the so-called softmax function, since we have 10 categories here. So this is something which we now can implement or study using TensorFlow with Keras. And I just wanted to show you how you can do that very quickly here. So if normally now if you use Anaconda, for instance, TensorFlow follows automatically. If not, there are just some simple instructions on how to implement or how to install it. And Keras is actually the APA which makes life a little bit simpler. So if you look at the MNIST case again, we are now just reading the data using the inbuilt scikit-learn functionality with data sets, and that just loads the handwritten numbers. So this is a data set with only 2,000 entries. It's actually less than 2,000. It's 1,800. And then we split it into train and test. And in total, we have roughly 1,800. It has 64 pixels, 8 times 8. This is the way the data set looks like. And then we transform that one into a design matrix, where we now have 64 input nodes, one for each image. And in total, we have 1,800. And then we split it in train and test, as we did. And here we are going to use Keras. So we are running this with a stochastic gradient descent with 100 epochs, a batch size of 100. We have now one layer with a so I'm going to run this calculation with two hidden layers. We have categories, which defines the outputs. And then we have 100 nodes here and 50 here. I'm essentially going to use the same activation function in each hidden layer. So here I'm simply setting my neural network with Keras. So I'm having a sequential model, because this is going to be a sequential process. We just move forward and backward. And we have a dense layer with 100 neurons, the sigmoid activation function. I have a regularization term, which has a norm 2. So this is the same as we would have with ridge regression. I have the second layer, and then here I simply have my output layer. So I'm adding now the different layers. You can look at the example here, and you see how I include all these different functionalities from Keras. So Keras is just an API, which allows us to set up this in a much simpler way. So it has an imports the input layer, it imports the dense functionality here, which allows us to set up a given number of layers. We import the types of optimizers, the types of regularizers, and then we want to have a categorical classification. So we are dealing with a classification problem here. So we have a different set of categories. And now I'm setting up my optimizers, which is now simply a stochastic gradient descent. This is a function of the learning rate. And I run this through different values of the hyperparameters. So you can see now the set of hyperparameters I'm using. So I have my learning rate eta, which goes from 10 to the minus 5 to 10 to the first. And the same with the hyperparameter lambda. And then I simply define the type of loss function I want to use, or cost function. It has the optimizer, stochastic gradient descent, and the accuracy is now my metrics, which I want to use. And here you can see when I've defined my neural network using Keras. This is very simple. And then I can simply run over the different learning rates and hyperparameters. And then I perform my optimization as a function of different eta values and lambda values. And finally, I fit my network with a given number of epochs and the batch size. And that reproduces, that gives me the scores. Oops. Let just a moment here. And then if you look at the training here, what I'm going to get now is actually something which is not as good as what I got with the simple calculation I performed with one layer. And you will see now that my training, I still get a training here with values of 1. But then when I look at my test accuracy, I'm actually at a test accuracy of 98%. In the previous case, I actually had 99%. So this could also have to do with the optimization function, which I use for the learning rate. So in this specific case, I just use a standard gradient descent, whereas in the scikit-learn case, I use the Adam optimizer, which is a default optimizer. But what you see in this case is an example of a case where you have one simple layer, which seems to be doing better than just adding 2 layers. So a model which now has an architecture with just 1 hidden layer seems to be giving a better result than a model with 2 hidden layers. And these are things which we have to play around with when we are running this type of calculations. So when we are running calculations with deep learning methods, we actually have to explore different number of parameters, like the number of hidden nodes, the number of hidden layers, the architecture, and also the type of optimization algorithm we use for the learning rate. So that means that our neural network calculation is in principle, or any deep learning calculation are in principle a set of calculations where we run many different numerical experiments. And then at the end, we have to select those results which give the best fit to the data which we have. So the training part, after we set up the algorithm and have all the functionalities we want to have, then the training part is actually the time-consuming part. And you can think of this in terms of Google's DeepMind project, since we're now staying with the Google's Keras platform. Then the Google DeepMind project is a project which in 2021 had a wage budget of $1.2 billion. And most of the expenses go actually to train different models and find the optimal parameters. That's a big fraction of the expenses with Google DeepMind's project, in addition to wages. So typically, for many problems, you can start with just 1 or 2 hidden layers, and that works fine. And then for the MNIST data, you can easily get the higher accuracy with just using 1 hidden layer with a few hundred nodes. And you could get something like 98% to 99% accuracy, which is roughly the kind of accuracy which humans are able to achieve on the same data set. So, which is not bad. For more complex problems, you can actually ramp up the number of hidden layers until you start overfitting the training set. And if you're dealing with very complex tasks, such as large image classification or speech recognition, that typically requires networks with dozens of layers. And they need a huge amount of training data. So it's often seldom that you train such networks from scratch. It is much more common to reuse parts of a pre-trained network that perform similar tasks. The question, there are many questions now, as you've probably seen. One of the questions is, which activation function should you use? The back propagation algorithm that works by going from the output layer to the input layer. and propagating the error gradient on the way. And once the algorithm has computed the gradient of the cost function with regards to each parameter network, it uses its gradients to update each parameter with a gradient descent step. So one of the problems which you face is that of vanishing gradients, and the other problem is that of exploding gradients. This is something which we will see a little bit later when we come to recurrent neural networks. So vanishing gradients is something which is specifically sensitive to activation functions like the sigmoid function, because when you have an argument to the sigmoid function which is very large or very small, then you have a sigmoid function which leads to values which are either 1 or 0, and then with these type of values, what you would see then is that the derivative is getting closer and closer to 0. And with the 0 derivatives of the activation function, then you can easily end up in a situation with vanishing gradients. And this was actually one of the, one of the bottlenecks in calculations of neural networks. And it wasn't until around 2010 that people actually made some significant understanding in why deep neural networks actually could lead to vanishing gradients. And this is very much as linked up with the derivative of the logistic function. So when people started to switch from the logistic function to other functions as activation functions, then one obtained actually much better result. And that led to an explosion in activities in deep learning. And there's a fundamental paper by Xavier Glorot and Hjorth-Jensen, which found that the problems with the popular logistic activation function and the weight initialization techniques was one of the main reasons for why neural networks could end up with vanishing gradients. And so that paper actually really sparked off the deep learning revolution as we've seen it. So you have many types of activation functions. We have this ReLU function we discussed earlier. We have also many variants of it. One is called the ELO function. So one of the things we actually want these activation functions to be is that they are continuous, they should be in a way bounded, and they have simple derivatives. So this ELO function is given by the exponential. There is a new parameter alpha. And then we have this the function, the variable z, when z is larger than equal than 0. And then it has this exponential when it's smaller than 0. And these are functions which often behave better than the standard sigmoid function with respect to vanishing gradients. So it's normally seen that it seems that, but you have to play around with it. So the ELO function is typically behaving better than this ReLU family of functions. And this ReLU function on average performs better than a tanh, which in terms performs better than the logistic function. So all these functions here have simple mathematical expressions which don't require too many floating point operations. And then they also have simple derivatives, because remember now that when we are training a neural network, we need to calculate derivatives again and again. And these derivatives, we would like them to be given by simple, continuous functions which are easy to implement numerically and don't require too many floating point operations. So we also want, so if runtime performance is actually an issue, then people normally use this ReLU functions or the leaky ReLU, which has values when z is smaller than 0. So the standard ReLU function actually puts the function to 0 when z is, the argument is less than 0. So that means that when you run a neural network experimentation or any of these deep learning experimentations, you would typically end up making many runs, testing different types of activation functions. So in most cases, people end up using the ReLU activation functions in the hidden layers. It is a bit faster to compute than other activation functions, and the gradient descent optimization does in general not get stuck with either exploding gradients or vanishing gradients. For the output layer, if you have a regression task, that means that you want to fit a function, a continuous function, you actually don't have any activation function at all. So what you feed in to the last output layer, the value z, is actually what defines the output. For classifications, you can use the softmax for many more than just 2 cases. So if you have a binary problem, what typically is used is a sigmoid function. So there are many ways to actually avoid some of the problems. So normalization is often done. So this is something called batch normalization that aims at addressing the exploding gradients and more generally the problem that the distribution of each layer's input changes during training. So the technique consists of adding an operation in the model just before the activation function of each layer, where you're simply zero centering and normalizing the inputs. You can use dropout, where you actually implement a pretty fairly simple algorithm at every training step. Every neuron has a probability P of being temporarily dropped out, meaning it will be entirely ignored during this training step, but it may be active during the next step. And that gives a new hyperparameter, which is called the dropout rate, which is set to 50%. Then, when you have exploding gradients, there's something which is called gradient clipping, which simply means that if the gradient is way too large, you just set it back to a smaller value. But normally what people do is to use this batch normalization. That's often used. So if you take a top-down view on neural networks, if we now look at the limitations of many of these deep networks methods, which often are more used with supervised learning, you need labeled data. So that makes it pretty expensive because you need actually to go through the data and have them properly labeled. There may be even human experts which label the data for you. These supervised neural networks, as we have seen now, without any reductions, they can become pretty large. We saw that in case of the MNIST data, where we had images which had been scaled down to 8 × 8 pixels. That gave us 64 input nodes. If we now have, let's say, 1 million images, and we have an image of 100 × 100 pixels, that means that we would have 10,000 input nodes with 1 million images, and that defines our design matrix. So that means that these methods are typically very data intensive, and we need more data when we are training. So the network normally can perform best when we have lots of data. They act on homogeneous data sets, which is also can be a limitations. And then we have the case that many problems are actually not about predictions. And in natural science, we're often interested in learning something about the underlying distribution that generates data. In this case, it's often difficult to cast this data in a supervised learning setting. So the answer to this one is more to use generative models, which we will not cover in this course. So we will mainly stay with deep learning methods like neural networks, convolutional neural networks, and recurrent neural networks. So this means that generative models like Boltzmann machines, so-called energy-based models, the operational autoencoders, generalized adversarial networks, and many other of the popular deep learning methods, which are normally embraced in a common denominator as generative models, is something which we will not cover here. However, with this kind of basic information about neural networks and deep learning methods, we are now ready to jump into the next topic, which is an application of these methods to something very interesting for us doing natural science, and that is the solution of differential equations. So this topic is something which we also will continue with tomorrow. So if we now go back to the material for today, if we just scroll up a little bit, I just wanted to show you how you now can use neural networks to solve differential equations. And we discussed in the previous lecture with the back propagation and automatic differentiation. And we are going to use automatic differentiation when we are setting up the solution of a differential equation. And We also looked at TensorFlow with some specific examples, and that's covered by the lectures from November the 27th. This is now session 8 under the list of our lecture notes. And automatic differentiation is something which we also discussed earlier. And you have the AutoGrad documentation, but automatic differentiation, or AutoGrad, which was the previous package, has now been replaced by JAX. So in the examples here, because we've had some problems with installing JAX on different platforms, is that automatic AutoGrad, which is no longer updated, it's actually been integrated with JAX, is a library which is a little bit more stable. So JAX is becoming more and more stable. So if you're having problems with running JAX on your laptop, then we would normally recommend to use AutoGrad. But AutoGrad is not being developed more. So JAX is the project which has taken over the further development of automatic differentiation. There are some notes on automatic differentiation and backpropagation if you're interested in looking up. But what I wanted to say something about now is actually how we solve differential equations with deep learning methods. And the basic philosophy is extremely simple. There are also some interesting examples of implementations in this master thesis, but you also have a book actually by Yadav and Kumar on how to solve differential equations with neural networks. So let's quickly remind ourselves a little bit of a typical differential equation. So if you now think of a general ordinary differential equation, would look something like this. So what does this actually mean? So let's go back to the whiteboard and take a quick look at a differential equation. So this F is actually me having collected the left-hand side and the right-hand side of a differential equation and just put them together. And then that means that the right-hand side has to be equal to 0. So let's see what we actually mean by that. And just look at this for a simple example. So when we are looking at differential equations, if we now take an ordinary differential equation, or ODE as they are called, ordinary diff equation, or ODEs. If we look at a standard equation, which we have seen several times, we would have a function f. So we have a df of d of x, and this can be given by a function g of x here. So this is the derivative of the function, and f is now a function of x only. So what we end up with typically is to define a new function L of x and g, which is simply given by df dx minus g of x, and we want that one obviously to be 0. So in the previous slide, what I showed you is actually a function which I label for f then, but in principle, this is just the difference between the left-hand side and the right-hand side. So what we also have, since we're dealing with an ordinary differential equations, we have some initial conditions. And these initial conditions are typically that we have an f of x0, which has some specific value, which I'm just going to label as of f of 0. So this x0 could be the first value. And normally you would, when you solve these differential equations, you have a huge set of different methods. With the simplest one is called Euler's forward integration method, or just Euler's method. So we would typically discretize the equations. This is a standard approach which we use. So that means that x goes over to a discretized variable, x of I, where this x of I would be given by some x of 0 plus some variable I times delta x. And this I goes typically from 0, 1, 2, up to a final value n. And this delta x would then be given by the final value x of n minus x0 divided by the number of integration points which we have. These are normally called either integration points or mesh points or grid points. They would have different names depending on the context. But normally they're called mesh points or grid points, or just discretization points. This means also that our variable f of x is now given by an f of x of I, which we would typically write as an f of I. And then that means that we would have something like an f of I plus minus 1, which is the same as f of x of I plus minus this delta x. And then Euler's method, which is the simplest possible method for calculating the derivative, is given by a df d of x, which is now approximated to f of x of I plus delta x minus f of x of I divided by delta x here. And this is normally written in a more compact way as f of I plus 1 minus f of I divided by delta x. This is the simplest possible update which we have of the function f. And if we collect this together, that means that I can find the next value, f of I plus 1, which is now given by f of I plus this delta x multiplied with the derivative of df dx calculated at x of I. And this would simply be rewritten as f of I plus delta x of f derivative at the value I. And in our case, this f of I derivative is given by this function g x of I, which we would rewrite as a g of I. So that means that the final algorithm is f of I plus 1, and this is given by f of I plus delta x times g of I, where this g of I here, this function here, this is a known function. Because we have, in the differential equation, we have simply now assumed that this g of x is a known function. But we don't know the function f. So what you see here is the standard recipe for setting up a differential equation and solving the differential equation. And then we can have more refined methods, like the family of Runge-Kutta methods, to solve this type of differential equations. If you're dealing with energy conserving problems, then you could use something like the velocity-Valère method or a modified Euler method, which is called the Euler-Kromer method, etc., etc. There's a plethora of such differential equation solvers. But this is the basic one. So what we are going to do now is actually to take a closer look at this using neural networks. So with neural networks, what we are going to do now is, and the philosophy, you will be surprised to see how simple this philosophy is. So with neural networks, we are going to discretize, obviously, the parameters. So there will be a set of discretized values x of i's. So we would have a set x of I, we will have a set of values f of I, and we will have a set of values g of I. Now, in our case, we are going now to approximate the function which we are going to integrate with a neural network. So the solution will now, solution is approximated with a neural network. What does that actually mean? So what it means now is that we are going to have a function, or function f, and we are going to have a trial function of x. So I'm just writing it like this. There will be a function which I'm going to call a function h of 1 of x, where often this h of 1 is tailored so that we can actually reproduce the boundary conditions or the initial value conditions. And then there is a new function, h of 2 here, which is given by x, the input value, but then it's going to be given by a neural network. So n here, this n stands for a neural network. And then we have a set of variables, theta, which are now the parameters of the neural network. So theta are the parameters of a neural network. Then we are going to define a cost function in order to be able to perform the optimization. So the cost function, which is going to be given by the c as a function of these parameters theta, that could be given by some 1 over n, which are the points we are looking at, from I equal 1 up to n here. And then I can have this function L here. And now it depends on how we're actually going to do it. So this L will depend on x. It will depend on this function, which we have defined as a derivative. So we have an f derivative. It can be a second derivative, etc., etc. And now we need to define how we want to calculate this. So we could actually let this be given by the square difference. So remember now that this function L, when we put it up, was given by df, the simple case which we had above, dx minus this g of x. So that means that we would start with a guess for f, and the guess we would start with f could be this neural network, where this h1 is now given by a function which respects the boundary conditions or initial conditions we have, and this function h of 2 here, which is now simply given by a neural networks and may be multiplied with something else. So we're going to look at specific examples. So we are making an ansatz for the function, and then we simply want to drive this difference between the left-hand side and the right-hand side of a differential equation, and we want to drive this to 0. So this, in a certain sense, looks like this kind of mean squared value, which we discussed in terms of ordinary least squares. But now what we are looking at is the difference between the left-hand side and the right-hand side, where we have assumed that the left-hand side of the differential equation is a known function. And then we are simply now, instead of performing the standard iterations you would get or integrations you would get with a finite difference scheme, we are now letting a neural network try to minimize the difference between g of x and the derivative of the function. This is the basic setup for the solution of a differential equation or a partial differential equation. So in the next lecture tomorrow, we will actually try to see how we can solve this type of equations. But the basic approximation is the one we have discussed here. We are going to replace the function or the initial value for the function with one function here which respects the initial or boundary conditions, plus something which depends on our neural network. And then iteratively, we are going to drive the difference between the left-hand side and the right-hand side of the differential equations. We're going to drive this to 0 by running through our neural network through a given number of iterations. And tomorrow we are going to look at study specific implementations of this, and we will see that neural networks actually give something which is competitive with the standard differential equation solvers. So we're going to stop here.